CUDA threats and occupancy would be the topic which we'll be covering in today's session of parallel programming. When you go for CUDA threads, blocks, and the GPU, we have already seen in the previous sessions of parallel programming of thread hierarchy, where we know that thread has been divided. You have a grid initially, and grid will contain multiple blocks, and each of the blocks internally contains a thread. And when you see this thread, this is a basic programming component which will make your code to work. We have even covered the software view and the hardware view of it, where coming to the hard software view, you have a grid initially. Grid is a collection of block, and block is in turn a collection of a thread, right? Now coming to the hardware part of it, when you go for your grid here, we call this as a GPU device or a kernel device, and we have a compute unit, or the other name given to the compute unit is nothing but your streaming multiprocessor. And beneath your streaming multiprocessor, we have a processing element, or we can even call it as a core. And we all know that core is a software component which will be executed, thread is a software component which will be executed on a core. And similarly, when you go for a blocks are being executed on a streaming multiprocessor. So this was a visualization or the relation between a software view and a hardware view. So in this CUDA threads, blocks, and the GPU, we see how this thread plays a major role in implementing your GPU programming. Having seen the previous one, now we will be seeing the same thing. So now when you go for your streaming multiprocess, we have multiple blocks present in it, and each of the block has multiple threads. Yes. Now coming to the streaming multiprocess again, when you go for this block as I told you is a collection of threads. So now we have seen a different unit of a thread which is nothing but WAP. WAP is nothing but collection of 32 threads, and this was a basic execution unit to be executed on your streaming multiprocessor. So even though you give a block to your streaming process, internally your block will be divided into WAPs, multiple WAPs, and each of the WAP will be executed on your streaming multiprocess. And sometimes they may be it is not compulsory that the WAPs are to be executed in the same order. You may have interleaving between the WAPs, and you execute the first WAP and then go for the third one and come back to your second one. But make sure that all these WAPs are corresponding to a single block, or these two blocks, if I name them as block 1 and block 2, they are to be executed only on the streaming processor, and these are block 3 and block 4. So assume this is your streaming multiprocessor 1 and this is streaming multiprocessor 2. At any cost, we have to make sure that block 3 and block 4 are executing only on your streaming multiprocessor 2. Even though you find the streaming multiprocessor 1 is empty, you cannot assign block 3 to your streaming multiprocessor 1. Whatever blocks are assigned to this multiprocessor, they have to execute that. So the basic execution unit is nothing but your WAP, where your block is divided into a combination of 32 threads. Now, the important thing we have to deal here is CUDA occupancy. Now, you have written a program where your blocks are divided into threads and you are assigning a thread to a core. But what is that? We have to be making sure that your GPU occupancy or the utilization of the GPU is done to the maximum extent. So, in order to know this occupancy, we go for using a formula where it is active WAPs which are being under execution, right, which are currently being executed, divided by the maximum number of WAPs that are being created. So this gives you a CUDA occupancy. And this CUDA occupancy can be calculated theoretically, or you can even go for achieved occupancy. Theoretical occupancy, as the name implies, it is nothing but your upper bound. Theoretical occupancy is your upper bound based on your hardware configurations, right, of the system. We just substitute the form values in the given formula and we get some value. So this can be known as a expected bound or expected values. So theoretical will give you the expected values, and when you run your program on in a real time, you will be getting some other differences, right? So that we call it as achieved occupancy. This is nothing but your actual values. So theoretical are nothing but expected, achieve are nothing but your actual values in a real time condition when you are making your GPU to work. Now, when you see this theoretical calculation of CUDA occupancy, this is basically done by using a CUDA occupancy calculator. So this is nothing but an Excel sheet uh, where for GP utilization we'll be using this. And when you see this particular sheet here, we have two parts here. One is nothing but the inputs what I need to provide and what is the output depiction that will be done on the sheet. So at the input stage, I need to provide my thread block size, registers per threads, and what is the shared memory per block. So these three would be provided as input, or we can even call it as a kernel information that we are providing it to the system. And once you provide these inputs, you get your outputs depicted either in the form of a graphical representation, what is the usage of threads per block, and this is the impact of varying the shared memory usage per block. So these are your graphical representation, how you are, as you are varying your block size, what is the depiction that is done, and what is the register per thread, registers count per thread when you are increasing, what is the depiction that is done. So these are graphical representation of changing the parameters. So this would be the output values given by a occupancy calculator. As I told you, we see in a clear way what is the compute capability of it, what is the shared memory size, right? And you can even specify the threads per block, registers per thread, shared memory per block. So these are all the inputs which you will be providing it to the system, and it gives you some value that is nothing but your upper bound. Now, we even have some visual profilers, NVIDIA visual profiler or some other graphical tools, or we call it as profiling tools. So using profiling tools, we calculate the achieved occupancy. Occupancy is nothing but we make the GPU work on a particular program and check what is the efficiency it is giving. So that is nothing but your achieved occupancy. So as you could see, this is one of the profiling tool which is giving me the both achieved occupancy as well as the theoretical occupancy. So theoretically, they claim that it should be 100%, but achieved occupancy is only 99.1. Can you just tell me why there is a variation between the theoretical and achieved occupancy? There are many parameters. So that parameters could be the number of blocks you are using for the program, number of VAPs you are dividing your blocks, number of threads that are active at that particular time, or the shared memory size, or you can even go for the register size. All these parameters will affect the occupancy of it. So why we are actually dealing with theoretical and achieved occupancy? So if you are able to find the difference between these two, you identify which parameter is being affecting and rectify those errors so that you can improve the occupancy of the system to a maximum extent. So this is all about your CUDA basic VAPs and the occupancy.